to our video demonstration of our project titled Path Delay Optimized Boot RADIX-8 Architecture, presented by KISHAN J. Project members are KISHORE P, SANJEET KUMAR, VIDHUR B PREMAN. Guided by Mr. T.R. Dinesh Kumar, Assistant Professor, EC Department, Tech. The Multiply and Accumulate Unit MAC is a main computational kernel in DIP architectures. The MAC unit determines the power and the speed of the overall system. It always lies in the critical path. Developing a high speed and low power MAC is crucial to using DSP in future WSN. In this work, a fast and low power signed MAC unit is proposed with reconfigurable modified boot algorithm. The proposed architecture is based on modified boot RADIX-8 architecture with merged 2's complement and MUX units with a low critical path delay and low hardware complexity. If you see at our project, as I said earlier, the MAC unit is such an important architectural board present for processors which are used in DIP and DSP applications. Since a lot of arithmetic calculation happens at this place, a MAC unit is often a determiner of the processor speed and the power consumption too. Since it always lies in a critical path, optimizing the MAC unit often ensures the most of the delays and other drawbacks of the processors are removed. The objective of our project is to propose a hardware-efficient RADIX-8 encoded MUX-based multiplier to minimize the path delay complexity of partial product deduction by using 2's complement computation in the early stage itself. To minimize the complexity through stage-wise reduction with some MUX unit to partial product carry propagation over direct iteration. In short, we aim to reduce the hardware required, to reduce the path delay caused by the system, and to also reduce the power consumption of a unit. In short, these are the three major drawbacks in which lacks every processor available. Now let us proceed to the demonstration of our project. We are using Quartus 2 for simulation of our circuit and Model Sim for verification of our project. Before proceeding, let us go to open the project in Quartus 2. After opening, press compilation. So you can see the compilation is going on. The Quartus 2 is mainly used here to synthesize our circuit based on Verilog program. We have used Verilog program and the compilation has been successfully synthesized. Now let us see each characteristic of our synthesized circuit. So as you can see, all the summary of report of synthesis has been given here. You can see number of elements used, and there are total number of registers, dedicated input registers, total number of I/O ports used, and all other information are mentioned here. Now let us proceed to one more characteristic. Let us see the synthesized circuit diagram using RTL viewer. Now the RTL viewer helps us to view the synthesized circuit. Here you can see we have used MUX based allocation. Here, as you can see, each partial product gets added and subsequently they are multiplexed into common signals, which are then again added for the final, which are again stored in the final registers. If you see the bird's eye view of the whole circuit, here's the whole MUX based registers and all the multiplexer which are combining the partial products here. The input section is shown here. And specific mux is shown here too. Now let's go to the next characteristic. Let us see the timing characteristic of our synthesized circuit. The timing characteristics, time-test timing analyzer. A specific timing analyzer for quarters 2 gives us many options and many other characteristics which can be seen. For example, let us check at the summary of this time test. You can here see the clock signal characteristics. And as you can see, there is a maximum voltage and the clock signal frequency which is generated. One of the main characteristics which we can check is Fmax. Fmax is the highest frequency in which our circuit runs. As you can see here, 221 MHz is the highest frequency this circuit can manage to work under. Often it is reduced further due to other delays, but as per our synthesized circuit, there is no such reduction. Now you can see that there are other reports here, and all the timing characteristics of each port and registers are seen here. Quarters 2 is a helpful tool in which it is comparatively similar to its other competitor Xilinx. Now let's go to the next section, power play. Power play is a power analyzer in which we are analyzing the power characteristic of our synthesized circuits. Let us start the simulation. The simulation here shows all type of power characteristics such as the static power consumption, dynamic power consumption. Now let us see the report. You see the total power consumption of this circuit is available as 68 milliwatts. You can see the dynamic thermal power consumption, static power consumption, and IO thermal power consumption. So all the three major types of power consumption is shown. So this is basically the circuit for the characteristics for our 8-bit RADIX boot multiplier, which actually is compared with other RADIX too. Like we are actually comparing with conventional multiplier and conventional boot 4 multiplier, and also the boot 4 RADIX structure. In order to verify our multiplier, I'm using a verification tool called ModelSim. For verification, let me open a new project. On opening the new project, enter the name of the new project, demo. Now we need to add all the related Verilog files using add existing files. All the required Verilog files. Go to your corresponding folder and add those Verilog files of your circuit. Now we have added all the files, Verilog files added. The next step is to compile all the Verilog files we have added to our project. Compiling all. Now after successful compilation, it's time to start this simulation of our circuit. Now we have added a test bench in order to manually give values as input to the following circuit. Now simulating the test bench. Now the simulation is running continuously. Now in order to see such values, we need to add all the simulated values to a waveform. Right clicking add to wave all items in the region will help you to plot the waveforms onto a graph. As you can see, they're all x values, which means the values from the simulation is not yet passed through the graph. Now we had to run the simulation for a specific time period, then break it in order to send the values. Running all, then simulate. Choosing the break option will give you the current value for the circuit. As you can see, there are two input values, x and y, which are the two numbers which are given in the input. Now the answer you see here is 24, which is the required output. 12 twos are 24. In order to confirm, I will show you the test bench. As you can see, I have inputted two numbers, 2 and 12, and the waveform, output waveform gives out as 24, which is our required value. Hence, the test bench values which we have inputted and the waveform values both are proved to be verified. Hence, our circuit is verified and the multiplier is working as such. Thank you for watching our video demonstration of our project. Welcome back. Thank you.